Hello class. So we're on 5.2, conservation of momentum in one direction. So last lesson we learned what momentum was, and I told you that one of the really useful things about momentum is that we can talk about collisions with it. And the most useful thing is this law of conservation of momentum. And that tells us that when two objects collide in an isolated system, the total momentum is conserved. Okay, and we have an equation for this. It is Pf, the final momentum, is equal to the initial momentum. And if we want to sort of write that in a longer way, with two objects, we can say m1 vi1 plus m2 vi2 is equal to, so this is the initial, it's equal to m1 vf1 plus m2 vf2, the final. So you can see there the initial equals the final. Now, this is really useful in a lot of situations, especially in lots of sports. You could probably imagine it being useful in pool, billiards, shuffleboard, and curling, and these sorts of things where you have these pucks that are hitting each other. But there's lots of applications. And so, so far I've been talking about collisions, but there's actually two types of interactions we'll look at. One of them is collisions. So these are the types of interactions we can work with here. Collisions and explosions. And I always like my explosions, so that's cool. We can look at explosions here. Now, we say that momentum is conserved, and in our physics problems it will be, but in real life we usually lose some momentum to outside influences. So here in real life, momentum is lost to outside influences, like friction and producing noise and sound. All these sources of energy loss, they're also sources of momentum loss. But in our situations here, we're looking at perfect conserved momentum. So we'll see two problems here. The first one talks about a hockey player. And it says a hockey player of mass 97 kilograms, skating with a velocity of 9.2 meters per second south, collides head-on with a defense player of mass 105 kilograms traveling with a velocity of 6.5 meters per second north. An instant after impact, the two skate together in the same direction. Calculate the final velocity of the two hockey players. So the idea is these two hockey players smash into each other, and in the end they end up skating off and like they end up moving in the same direction at the end because they've collided together, and that's the result. Or they've become friends and they're holding hands. I don't really know. But this is our momentum. So we just use our statement. We say that the final momentum, the total final momentum, has to equal the total initial momentum because it's conserved. And, well, if I want to find my initial momentum, we know that we had a hockey player that was 97 kilograms. M times his V. Well, maybe I'll write out the statement here first. So this is equal to M1 V I1 plus M2 VI2. Okay, now we can plug in some numbers. We have 97 times 9.2 plus, and our other player here is 105 kilograms times 6.5. Now this 6.5 is in the opposite direction, so I'm going to say negative 6.5 because it's going north, the other one was south. Okay, and this gives us 210 kilogram meters per second, and our direction that we chose here was south. Good, so that's our initial momentum. That means that our final momentum has to be the same thing. So we also know that the final momentum, well, we can say the final momentum is equal to that, 210 kilogram meters per second south. And it is also equal to the m1 v1 plus m2 v2. Now in the end they're going the same speed, so I can say m1 plus m2, they're going together with this same vf. And we want to find what that final velocity is. So we can rearrange this equation. Vf is equal to our final momentum divided by m1 plus m2. And now we can just plug in some numbers here. So we had our final momentum, 210, divided by m1 is 97, plus m2, 105, and this gives us 1.0 meters per second south. That was our total initial momentum. This is our total final momentum. There we go. That's our final answer. Now you can see this is fairly easy because we're dealing just in one dimension, but you can see that we could have two-dimensional problems just with vector addition as well. Okay, now second page here. It says, in a science fiction novel, a large asteroid is approaching Earth. Scientists decide to explode it into two halves before it hits the Earth. The asteroid has a mass of 2.4 times 10 to the 9 kilograms. For each half to safely miss the Earth, they must travel a minimum of 8 times 10 to the 6 meters at a right angle away from Earth within 24 hours. Okay, first thing I'm going to say is your handout is going to have a picture. I forgot to put the picture onto this handout. So it's got a picture showing what's happening. We've got this asteroid. Here's the Earth. Here's the asteroid coming here. And we want to split it in half. And it's going to be going up, and it's going to be going down. It's going to be splitting in half like that. So, going on, it says assume this is a one-dimensional problem, so we're just splitting it up and down. The magnitude of the impulse applied to each fragment is the same. You remember impulse from the last chapter. Okay, part A. We want to calculate the momentum of each part of the asteroid after the explosion. So again, we have our asteroid. Each piece is going to be needs to be going up this far, 8.0 times 10 to the 6 meters. That's how far up it needs to go to clear the Earth, and it needs to do that in 24 hours. Okay? So we have a speed. It needs to cover that distance in that time. So we can say that for one of our two halves, the speed needs to equal 8.0 times 10 to the 6 meters over 24 hours. That's how fast it needs to move. And to get those in good units, we can say 1 hour is equal to 60 minutes. And then we can do that again. We can say 1 minute is equal to 60 seconds. And this gives us 92.6 meters per second. Good. So that's our speed. Now all we need to do, we just need to find the momentum. Well, momentum is equal to mv. Our mass, we're only dealing with half of this asteroid, so we can say m is equal to, instead of 2.4, it's 1.2 times 10 to the 9 kilograms. And now we just need to put in some numbers. We've got 1.2 times 10 to the 9. And our speed is 92.6 meters per second. This gives us 1.1 times 10 to the 11 kilogram meters per second. Excellent. And last piece here, determine the impulse delivered to each part by the explosion. Well, remember impulse, it's this guy. That's delta p. It's just the change in p. So we can say it's the final momentum minus the initial momentum. Okay. Well, we know our final momentum. And the initial momentum, it started off not moving at all. So we just have 1.1 times 10 to the 11. That's our final momentum. And our initial momentum was 0. So easy enough. We just say that our impulse is the same value, 1.1 times 10 to the 11 kilogram meters per second. Excellent. Now, maybe we want to write that in our impulse units instead. So that's 1.1 times 10 to the 11 Newton Newton seconds. That's right. And there we go. That's the whole topic. Oh, one last tiny little bubble here. Rocket propulsion. No math for this, but just to point out, we've talked about rockets before in terms of Newton's second law. It pushes out or actually Newton's third law. It pushes out the fuel and gets the reaction force. But rocket propulsion, we can say it relies heavily on conservation of momentum. So I was saying it's the conservation of energy, but also conservation of momentum is important here for rocket propulsion. So it burns all this fuel, pushes it out. Now, one problem with trying to do math on these rocket problems is that as you burn the gas, the mass of your rocket decreases as you go up. And for that sort of thing, I'll say which requires calculus. Requires calculus. To deal with a situation where our mass is changing as we go, we would need to use calculus. So that's why we're not going to see those sorts of problems really in this, but they would be cool problems to deal with if we could do that calculus part. All right, that's all we have to say about this topic. Thank you very much.